Now let us look at the definition of a plane at infinity, and it has a canonical position of pi represented by pi infinity equals to 0, 0, 0, 1 here. So we can see that this is a direct extension of the line at infinity, which is on the 2D projective space, which is given by 0, 0, 1 transpose, and this is in the P2 space that we have defined earlier. And in this case here, the plane at infinity is in the P3 space, is in the projective 3 space. We can see that this is another example of a direct extension from the 2D space into 3D space. And it contains the directions, all the directions of these ideal points, x1, x2, and x3, and 0 here. So what this means here is that at the plane of at infinity, the plane at infinity denoted by pi infinity here, which is given by 0, 0, 0, 1 here transpose. It contains all the points that are contained in this plane at infinity are the ideal points in the P3 space here, and this is denoted by D, which is equals to x1, x2, x3, and 0 transpose here. And these are the representing the directions that are pointing from the finite space to the infinite space. And this enables us to identify the affine properties such as parallelism, particularly two planes are parallel if and only if their lines at intersection is on the plane at infinity. This means that if I have two parallel lines, and this would be going to intersect at the infinite point, which is given by D here, x1, x2, x3, and 0 transpose here. And this has to be lying on the plane at infinity, since this point at infinity, the ideal point is going to lie on the plane at infinity. This means that two lines or two planes are parallel if the line are intersecting at the plane at infinity. And similarly, a line is parallel to another line or to a plane if the point of intersection is at infinity. So in the first case, we are looking at two planes. In the second case, we are looking at a line and a plane. This is the top view of the plane, for example, and they are going to be at parallel, and they are going to intersect at this ideal point here. Now, the plane at infinity is a fixed plane under projective transformation H, if and only if H here is an affinity metric or affinity transformation metric. And here we can, the simple proof to show this, we have the plane at infinity. This is going to be pre-multiplied by HA inverse transpose. This is now a 4 by 4 transformation metric, and this guy here is going to be a 4 by 1 homogeneous equation here, or homogeneous coordinate representation of the plane in the P3 space. So now we can substitute this HA into this equation here, and the pi of infinity is going to be here. So we can see that the evaluation of this would give us the plane at infinity again. Hence, this proves that the plane at infinity remains fixed, or we say that it's invariant to the affinity transformation. Here's two remarks. The plane at infinity is general fixed under affinity, but not fixed point-wise. So it's the same as the line at infinity, where we actually, after the fine transformation of the line at infinity, line at infinity still stay at line at infinity, but the points x1 and x2 here, we say that it could change order here, or it can change location, the relative location, but they are all going to still be collinear here. And in this case here, we have the plane at infinity, pi infinity here. After it undergoes a certain affine transformation, this plane at infinity will still remain at plane at infinity, but the points inside here, they might change location, but they are all still going to be contained inside the plane at infinity. And the second remark here is that under a particular affinity, for example, a Euclidean motion, there might be planes in addition to pi at infinity which can be fixed. So what this means is that under a certain HA here, affinity metric, in addition to pi and infinity that will stay fixed under the transformation of HA, there could be also other planes here. For example, pi I that undergoes this HA here. It could also remain fixed under this affinity. And however, only pi infinity is fixed under any infinity matrix, affinity matrix of HA. So any affinity matrix will always, the pi and infinity will always be invariant to it. But there might be some uh, planes in the P3 space that can be invariant to some affinity matrix. So here's an example of the affinity matrix where there are a subset of the planes that can be invariant to this transformation here. So this is a Euclidean transformation which we have seen earlier, and it's denoted by this particular matrix here. So what it means here is that I'm rotating around the z-axis here. So that's why the last column here of the rotation matrix here is going to be 0, and there's no translation here, hence the last 3 by 1 vector over here is going to be 0. And we can see that this particular transformation, Euclidean transformation here, this plane here that is being rotated, it's going to stay invariant, because after rotation and before rotation, it's still going to be the same plane. But what happens here is that we can see that it's fixed as a plane as a set, but not point wise, because we can see that the points here with respect to the original axis, the representation is going to move, is going to change here, is going to be transformed to another point here. It's going to rotate in a circle by this Euclidean action over here. And algebraically, the fixed planes are actually eigenvectors of the homogeneous transformation H transpose here, which we can see from this equation here. This is the proof here. So what we are doing here is that we are going to transform a certain vector here, a certain point on the plane, or a plane over here, denoted by V. This is a 4 by 1 homogeneous coordinates that represent either a point or a plane here, and we are going to transform here. So in this case here, this is a plane, V is a plane, and we are going to transform by H inverse transpose, and this is going to be equivalent to lambda of V over here. So what this means is that we are simply going to just scale this plane over here, but it's still going to be the same plane. And we can see that this is actually our famous eigenvalue or eigen equation in linear algebra, where we say Ax equals to lambda of x over here, where x here is actually our eigen vector, and lambda here is our eigen value. So in this case here, after this projection or after this transformation by A, x, which is the eigenvector, is going to be scaled, but it's not going to change direction. And this is the definition of eigenvectors here. So as a result, what we can see here is that the plane here, in this case, this kind of planes here, and the H transformation here would form the eigen equation here. And what this means is that for any plane that is an eigenvector, we need to find the H over here, the projective transformation, such that the decomposition of this, or such that V here, the plane, is the eigenvectors of H, the transformation here. Then this set of planes would remain invariant to the transformation given by H over here. And we can see that we can substitute V here by pi, which is our plane equation, and this would exactly form the transformation, where lambda and V here are eigenvalues and eigenvectors of the H transpose and H inverse transpose respectively. And in this case, the eigenvalues, or in the example that we have seen to rotate around the z-axis, in this case here, the eigenvalues and eigenvectors of this guy here, which is the equation that we have seen earlier here, the matrix, it's given by four components here. Since this is a 4 by 4 matrix, it would have four eigenvalues and four eigenvectors here. And these are the four vectors that we have seen from that we can get from this particular matrix over here. And in this case here, these four eigenvectors, two of them are imaginary and two of them are the real eigenvectors. So we'll ignore the imaginary planes E1 and E2 and focus on E3 given by 0, 0, 1, 0 and E4 that is given by 0, 0, 0, 1. And we can see that E4 here is actually our pi at infinity, the plane at infinity. And E3 here directly corresponds to the z-axis, which we are rotating around. So this is the normal vector of a plane stays invariant after the affine transformation along or around the z-axis. And interestingly, we can also get a tensor of fixed planes that is spanned by E3 and E4 because we can treat these two as our basis vector to get the linear combination of it to get new planes or additional tensor of fixed planes that are fixed under the transformation of H. And we say that E3 and E4 are degenerate planes here. So we can see that the axis of this pencil is the line of intersection of the planes that is perpendicular to the z-axis. So this is the E3 given by E3, where E3 is actually equals to 0, 0, 1, 0, and that represents the normal vector of this plane here. And the intersection of this plane with the plane at infinity, pi to infinity, which is given by E4 here, it's given by 0, 0, 0, 1 over here. So the intersection between these two planes here, it's going to give us the line that represents the intersection or represents the tensor of planes that is invariant to the projective transformation H that we have seen earlier. And this forms the line equation, or this particular line here at the plane of infinity. It's given by the span of E3 and E4, which is what we have seen in the previous lecture, and of the definition of a line in the 3D space. And what's interesting here is that the null space of this line is the null space basis of of 1000 and 0100, which denotes the infinite point or the point at infinity, the ideal point on the both the line at infinity as well as the plane at infinity. And linear combination of these null space bases will give us all the points on this particular line here at infinity that intersects the two planes of z that rotates around z as well as the plane at infinity. And we'll see in lecture 6 that uncalibrated two-view reconstruction. This means that if I have two views, two images from two different viewpoints of the same scene, I can get the relative transformation, rotation, and translation here. And then after that, I will be able to do triangulation. This is when we look at what is called the fundamental matrix and the triangulation algorithm, and we'll be able to recover the 3D structure up to a certain projective ambiguity. And by making use of this plane at infinity, we'll be able to recover or remove the projective ambiguity and recover the scene with a affine ambiguity here. And then by using And we'll see that how this can be done using the plane at infinity in lecture. And we'll see how this can be done using the plane at infinity in lecture 6. Now, let us look at the definition of absolute conic. Previously, we looked at the circular point, which is a line at infinity. Any circle or any conics that intersects the line at infinity will always be at the 2 points of circular point I and j. And now we will look at the definition of absolute conics, which is the conic denoted by omega infinity, it's a point conic on pi of infinity. It means that it's actually a conic that is on the plane of infinity. So any conics that lies on the plane of infinity here, a conic that lies on the plane of infinity, is known as the absolute conic, denoted by omega infinity. And in metric frame, we know that the homogeneous coordinates of pi infinity is given by this vector over here, and the points on omega infinity, absolute conic, would satisfy these two equations here. So this means that it's also a complex number. X1 square plus x2 square plus x3 square is equals to 0, and the fourth element here is always going to be 0. So we need two equations to define omega infinity, or the absolute conic. And for directions on the plane at infinity, that is points with x4 equals to 0, the defining equation can be given by this equation here. So this essentially is the first part of the two equations, x1 square plus x2 square plus x3 square equals to 0. Since this guy here is identity, it's a 3 by 3 identity given by 1, 1, 1, and 0 at the off diagonal. And so the absolute conics omega infinity corresponds to the conics with matrix C equals to I, and this is a conic of purely imaginary points on pi at infinity. What this means is that it actually doesn't exist physically. We won't be able to see it in the real world because these are purely imaginary points. And the conics, it's a geometric representation of 5 additional degrees of freedom required to specify metric properties in an affine conic. So one of the properties of the absolute conics is that it must remain fixed under projective transformation H, if and only if H is a similarity transformation. Here's the proof of this invariant of the absolute conic. So since the absolute conics lie on the plane at infinity, pi infinity here, a transformation on it must fix pi at infinity. This means that a transformation of the absolute conic, since it lies on the plane at infinity, this particular absolute conic here, omega infinity, a transformation of it still must lie on the plane at infinity after the transformation H. So what this means is that we know that this guy here, omega infinity, after the transformation, it still must lie on the plane at infinity, and as well as we have seen earlier that the plane at infinity, it will remain fixed under the affine transformation. Hence, this transformation here that transform omega infinity, for it to remain the same, so for omega prime to be equals to omega itself infinity, then this particular H over here must be an affine transformation in order for pi infinity to remain fixed under this transformation. Hence, we can write this affinity transformation to be this guy over here, where A here is actually our 3 by 3 matrix and T here is a 3 by 1 vector. And at pi infinity, omega infinity is given by the identity matrix. We have seen this earlier, that it's going to be x1, x2, x3, and multiplied by identity as well as x1, x2, x3 to give the first equation to be 0. And hence omega infinity is equals to identity at pi of infinity. And since it's fixed by this guy, the affinity matrix, because we want pi at infinity to also remain fixed, then this means that A inverse transpose I A inverse, which is the transformation that is on the conics, must be also equals to identity. Since I here is our conic omega at infinity, and the transformation A applied on it must bring it back to infinity. And taking the inverse of this guy here, by computing this, we can see that we get this A multiplied by A transpose equals to identity expression over here. What this means is that A inverse must be equals to A transpose, and this is the octagonal relation of the rotation matrix that we have seen earlier when we talk about rigid motion in 3D. And hence, this A here must be a scaled rotation, since the scale doesn't matter here. And with reflection, and as a result, we prove that this particular affinity matrix here, A must be a scaled rotation. It must be a rotation, and hence we have proven that this HA here must be a similarity transform, and therefore the absolute conics will only stay fixed under similarity transformation, where this similarity transformation will also fulfill the invariant property of the plane at infinity. And even though the absolute conic does not have any real point, it shares the property of any other conics. So the conics is absolute conic is fixed as a set in general, and but it's not fixed point wise under any similarity transformation. This is the same as the plane at infinity. It's fixed under affine transformation, but not pointwise, as well as the line at infinity. And one remark that can be made here is that this means that under similarity transform, a point on pi on the omega at infinity may travel to another point, but is not mapped off the conic. This means that given this conic on the plane at infinity here, this is omega infinity, a point here after any similarity transformation, it might be mapped off the conic, but it will not be outside the conic. It will still remain inside the conic. And the second property here is that all circles intersects omega infinity at 2 points. And the remark here is that suppose that the support plane of the circle is pi. So any circle in the 3D space or in the projective 2D space here, support plane is pi, and this intersects the another plane at the plane at infinity here, which contains our absolute conics over here. So this guy here is going to intersect at 2 points. It must always intersect at the absolute conics here at 2 points, and then pi intersects the plane that contains this circle must intersect pi at infinity at a line here. It must intersect at a line, and this line intersects this conics here, absolute conics here on 2 points, and these 2 points must be the circular point I and J that we have defined earlier. And all spheres intersect the plane at infinity. So if I have any 3D sphere here, it's going to intersect the plane at infinity on the absolute conics given by omega infinity here. So similar to the circular point, we can make use of the absolute conics to define the angle between any two lines in the projective 3D space. Suppose that I have two lines given by D1 and D2. It's a 3-vector directional vector. In this case here, D1 and D2 are actually my ideal point that is pointing towards infinity. So because recall that all the points at pi of infinity are actually directional vector. It's pointing towards the point at infinity, and hence I can also make use of this to represent the line directions D1 and D2. So this line here D2 is going to point to another point at infinity, and the dot product of these two directional vector will give me the angle between these two lines direction. And here we can elegantly define this under any projective transformation to use the absolute conics here to represent this dot product over here, where D1, D2 are ideal points, or the directional vector that intersects the plane at infinity at the ideal point. And omega infinity here is the matrix representing the absolute conic in that plane. So these two intersections here must intersect at the absolute conics that is contained on the plane at infinity, and omega infinity is that absolute conic in that plane. So the two directional vectors are octagonal if this relation here gives us 0, which means that we have a cosine of 90 degrees here, and this would be equals to 0 here if these two lines here, the directional vector, are perpendicular to each other. We'll see in lecture 5 that this image absolute conic can be used to recover camera intrinsics, as that is to use it for calibration. Furthermore, we'll also see in lecture 6 that the absolute conic and the plane at infinity can be used to remove the affine distortion here. And after we have done the reconstruction, we can remove the projective ambiguity and then make use of this conics, absolute conics here, to remove the affine ambiguity, such that we will be able to recover the 3D reconstruction up to a certain scale. Now, after looking at the definition of the absolute conics, let's also look at the absolute dual quadric. So this is the dual of the absolute conics. The dual of the absolute conics is a degenerate dual quadric in the free space called absolute dual quadric, and we will denote this with Q infinity star. So geometrically, Q infinity star consists of planes tangent to the absolute conic. So recall that previously we have defined the conics, the absolute conics, to be point conics, and the dual would be defined by planes that are tangent to the absolute conics. So previously this guy here, omega infinity, is defined by all the points that are on the conics. Now we are going to look at the planes that are tangent to this conic can be used to define the absolute conic, and we call this the absolute dual quadric. And this is the rim of the, it can be thought of that this guy here, the absolute conic, is the rim of the absolute dual quadric, which we also call the rim quadric. So algebraically, the absolute dual quadric is represented by a 4x4 homogeneous matrix with rank 3, and the canonical form is given by this guy over here. So as in comparison to omega infinity, the conic is just an identity matrix, and in this case here is given by identity with padded columns and rows of zeros. And the dual quadrics is a degenerate quadrics. There are 8 degrees of freedom because it's a symmetrical matrix with 10 independent elements, but the irrelevant scale and determinant of 0 will have to take off 2 degrees of freedom from these 10 independent elements here. That gives us 8 degrees of freedom here. And the absolute dual quadric is fixed under projective transformation H if and only if H is a similarity transformation. So this is the same property as the absolute conics. Since it's a dual of the absolute conic, it must follow the same property. So now let's look at the proof of the absolute dual quadric when it's undergoing similarity transformation, and it will remain fixed. So since this guy here is a dual quadric, its transformation is given under this equation, and applying this with an arbitrary transform, which is given by this guy over here. So this is HP, HA, and HS over here, and we will get this identity, which is our absolute dual quadric over here, Q infinity star, and this is also our Q infinity star over here. So what this means is that if we were to apply it with a general or arbitrary projective transformation given by the product of these three factors over here, we'll be able to get this equation over here. And this must be, in order for the absolute dual quadric to remain fixed, this means that this equation here, the matrix over here, must be equal to the absolute dual quadric after the transformation. And the proof here is that in order for this guy here to be identity A and multiplied by A transpose here, it must be a octagonal matrix or scaled octagonal matrix. This means that it must be a rotation matrix followed by a scale, as well as these terms here must be all 0. And this, we can see that this will all be 0 if V is equals to 0. And V, it's the is the last three by one element of the of our transformation of the projective transformation v and the vector here and a small v over here. So what this means is that in other words, H must be a similarity transform. Since A here it must be it must be a scaled rotation, and V here must be 0. This means that H must be a similarity transform given by this guy over here, T and then 0 and 1 here. Another property of the absolute dual quadric is that the plane at infinity is the null vector of the absolute dual quadric. So a remark here is that this can be easily verified when Q at infinity, this Q infinity here has its canonical form in the metric frame. And with pi at infinity given by this guy here, we can see that uh, the product of these two will give us 0, which means that the pi at infinity is actually an incidence of q at infinity, which is given by I 0, 0, 0, and multiplying it by 0, 0, 0, 1 here would give us 0 here. And this property here holds after any, regardless of the uh, transformation that is applied on the pi at infinity as well as the absolute dual quadrics. We can see that this is true if after the any projective transformation given by H over here that transform a point in the 3D in the P3 space, then Q is going to be transformed to Q prime and pi is going to be transformed to pi prime over here, undergoing these two transformation. Putting it back into the incidence relation, we can see that all the H essentially cancels off and remaining with one H over here, but we will still get back this equation over here, which is equivalent to 0, and the whole thing will be equals to 0. Now, the angle between any two planes, pi 1 and pi 2, is given by this equation over here. And this is dual to the absolute conics. So we can get this relation over here. And the proof here is that consider two planes, pi 1, we have the normal vector and the distance, and the normal vector as well as the distance. And in the Euclidean frame, the absolute dual quadric has this particular form here, and we can get cosine theta equals to the dot product of this normal vector equals to this. And by inserting the this guy over here into this, we can also consider D1 over here, and where D1 is eliminated by the 0 paddings in Q infinity here to get back this particular equation. So we can prove that these two are equivalent here, and which is the angle between the planes expressed in terms of the scalar product of their normal vectors. Now a remark here is that if the planes and Q infinity are projectively transformed, then the angle here will still remain the same due to the transformation properties of planes and quadric. So I leave this as an exercise to prove, for you to prove. Basically, you just insert all the H, which is representing the projective transformation, into this equation here and show that it actually cancels out each other. So now in summary, we have looked at how to use the line at infinity and the circular points to remove affine and projective distortion. Then we have looked at the how to describe the plane at infinity and its invariance under affine transformation. Finally, we describe absolute conics and its absolute dual quadrics and their invariances under similarity transform. We will defer the use of absolute conics as well as the absolute dual quadric and the plane of at infinity for affine and projective undistortion in 3D space until we look at camera calibration as well as the fundamental matrix in lecture 5 and 6 respectively. Thank you.